I want to quickly kind of go over the calculations for the Keq Lab. But the bottom line is you really have to go through this, put the effort in, and sort this out for yourself. So I'm going to try to give you some hints and some overview of what's going on, but you're just going to have to slog through this, read it carefully, work the calculations, and make this make sense for yourself. There are two reasons why we're doing these calorimetry measurements. One was we wanted to take a standard solution and make that little calibration curve that we were doing. So remember, we're doing concentration versus the absorbance. We were able to graph, and so if we know the absorbance of a sample, then we can figure out what the concentration is. So that's one big piece of this. But the other part of this was that we wanted to go through and set up 5 different equilibrium situations and calculate for ourselves what were the equilibrium concentrations of the different chemicals, substitute them back into the Keq value, and therefore we could calculate what the Keq is for the FeSCN equilibrium, like we see right here. So that's the overall objective, is to come up with a Keq value for this equilibrium system. Well, we start off here with the idea that we're going to mix together, one group of people were working on mixing together standard solution. Well, to make a standard solution of this was a little bit tricky in that we had some iron nitrate solution, and even though it's iron nitrate, the nitrate for us is a spectator ion. We don't concern ourselves. So we say this is Fe3 plus solution. We had another solution that was potassium thiocyanate, and again, we're not really concerned about the potassium, it's the thiocyanate solution. And when those mix together, it turns to this reddish-brown FeSCN solution. But what I'd like you to notice is that this is a 0.0002 molar SCN minus solution, but this is a 0.2 molar Fe3 plus ion solution. In other words, this iron solution is 1,000 times stronger than our SCN minus solution. So if we're saying here I'm going to mix together 2 milliliters and 8 milliliters of my two chemicals, it's kind of more like you're mixing 2 milliliters with 8,000 milliliters of the iron. So you can see what's going to happen. It's going to totally drive this reaction to the right by Le Chatelier's principle, and essentially there will be no SCN left in solution. It will all turn into the FeSCN solution ion. But the other part of that is, if we know the concentration of the SCN minus by doing our calculations, then we essentially also know the concentration of the FeSCN. So we're going to take our 5 solutions, figure out what is the SCN minus concentration, and to just say that that is the same as the FeSCN2 plus solution, and then go back and do our graph. So we have the concentration of the FeSCN 2 plus, and we're going to calculate, we're going to measure the absorbance and then plot those values. So plotting those values, and remember when you plot them, include that 0 point, and that way anytime we can measure some sort of absorbance for a chemical, then we can find out what concentration that chemical is. That's very important. Now moving on. If we have a situation, let's say 8 milliliters of iron, 2 milliliters of the SCN, well, how do we get that concentration of the SCN, and therefore concentration of the FeSCN? And the idea is that we're going to use the dilution formula. And dilution formula we have written right here. The volume times the molarity before you dilute is equal to the volume times the molarity after you dilute. So in our first situation, if I said I have 2 milliliters of my SCN and its concentration is 0.0002, I can't use that number because once I mix my 8 and my 2, now my new volume is 10 milliliters, so I need this answer here, the concentration of the diluted solution. Now you can see the math of this is very, very simple, because I need to solve for x, so I'm going to have 2 divided by 10 times 0.0002. So the fact that this is milliliters and this is milliliters, that's going to cancel. So I'm just saying that 2/10 of my solution, since I started with 2 and I ended up with a total of 10 milliliters, 2/10 of my solution times the concentration of my solution gives me my final answer. So that is officially the SCN minus concentration, but it is also the FeSCN2 plus concentration because we use so much iron, all of our SCN has turned into FeSCN2 plus. So you can see what's going to happen is you have taken that first recipe and calculated now that this concentration is 0.00004 molar, and let's maybe double check that, yes, 4 zeros and a 40 molar, and then because you use the colorimeter, then you know what the absorbance is, so you're going to plot your values. So of the different concentrations you get, you're going to plot the values. Don't forget to use 0, 0, and that'll be your calibration curve for the FeSCN. So this is concentration of FeSCN 2 plus, and this is the absorbance on the y-axis. And now if you happen to know a concentration, like in part 2, you're going to be able, if you know an absorbance by measuring the sample, you can tell what the concentration is. Now, for the second part, and the big part of the lab, is we were trying to figure out what is the Keq value for this equilibrium. The Fe3 plus SCN minus turns into FeSCN2 plus. So we want to figure out that value. Well, the way we're going to do it is we need to get values for this, and this, and this, and substitute them into our expression and see what answer we get. So we're going to set up 5 different equilibrium situations. And on this time, notice again, we have iron nitrate, we don't care about the nitrate, and we have potassium thiocyanate, but they are both 0.002 molar. Okay, these are much more equal now. And we're going to put together 5 milliliters of our iron solution with 1 milliliter of SCN minus, and then just to make everything equal, we'll put in 4 milliliters of water, so we have 5 milliliters of each of our 2 solutions. So our ending solution will be 10 milliliter sample, and all we have to do then is say, well, what is the iron concentration? Okay, it is not going to be 0.002 because we just diluted it by adding it to the other solution, so it's going to be 5 over a total of 10 times 0.002. So we can see then again our molarity is equal to our volume before we start over the volume when we're finished times the initial molarity. And so in this case here, to be 5 over 10 times 0.002. So the Fe3 plus concentration is simply going to be 0.001 molar. And that's very convenient. And you can see what's going to happen since we have 5 milliliters all up and down, and by adding the water it's always 10 milliliters, then this is going to be a same concentration for all 5 solutions. So that part's easy. Now for the other one, okay, we have to do the SCN minus. Well, we can see what's going to happen. It's going to be 1 milliliter over a total of 10 milliliters. So 1 over 10 times its initial concentration, 0.002, and then that'll give us our SCN minus concentration. So 1/10 of 0.002, 2/10 of 0.002, 3/10 of 0.002, over and over and over. Now we take those values and we go back and we put them into our chart. So you've just calculated values like this, and when you made that solution you checked its absorbance, and now you can use your calibration curve. So you can say, okay, I know it had this absorbance, so therefore I know this is the concentration of my FeSCN. So this value is going to give me my FeSCN concentration, and these 2 values you're going to get those by doing your dilution, and you measured this one. And you can repeat that for 6, 7, 8, 9, and 10. Final thing is to go back now and work on your Keq calculations. So what we did was, when you did the dilution, then you were calculating the Fe3 plus ion and the SCN minus ion, and then using your data you figured out the final concentration of the FeSCN. So we know that this is 0. Now if you know this value, if you know the initial and you know the final, then you can figure out this one. And if you know any one of these three, you can figure out all three of those. And if you know your initial and your change, then you can calculate these values. And it turns out these are the three values that you're going to put into your Keq expression and come up with a value for Keq. You'll do that for solution 6, 7, 8, 9, 10, and then following directions figure out what is the deviation in that data, because hopefully those values come out to be very, very close because they're constants, the Keq constant. And then you can go on and work on the questions. Good luck.